Yeah. So I mean, I have to start with just kind of a warning. I mean, this is mainly was meant for my class. So it's very simple statistics, and part of my goal is to show the students that some very simple principles of statistics can be relevant to real life. So of course, we are all now interested in this question of vaccinations for the COVID and how effective they are. So we can use this as a motivation to demonstrate some very simple principles, but there is no novel new research here. It's just applying simple principles to understand what's happening with those announcements about the COVID, about the vaccinations. Okay, so let me start with my so this is my talk, and it's about the statistical significance of the, when I wrote it, it was just Pfizer, now it's Moderna also, and we want to analyze how significant it is, and it was based on discussions that I had with my colleague Nati, who is a statistician, and his wife Ellie, which is a biologist. Okay, so does it move? Okay, so what do we know? So we know what was published is that Pfizer had an experiment that included 44,000 participants, and they randomly gave half of them the vaccine, and the other random half got the placebo. And of course, the participants didn't know which one they are getting, and so also the people that evaluated how well they were. And then they were asked to report if they have symptoms. And if they had symptoms, so once a week, they were calling them and asking them about how they feel. And if they had symptoms, they were tested for COVID. And during this period, it started in June 27 until they announced it. 94 participants in the Pfizer experiments were found to have COVID-19. And only 8 of those were from the half that received the vaccine. So that's the result that they announced. Out of those 94 participants that were sick, only 8 belonged to the half of the population that got the vaccine, and that looks very encouraging. Similarly, if you look at what happened in the Moderna experiment, they included 30,000 participants. Again, random half of them got the vaccine, the other random didn't get. Everything was a similar procedure, and in that case, they got 95 participants were found with COVID by the day that they announced the results, and only 5 of those 95 were among the half that received the true vaccine and not the placebo. So what we would like to find out is, if you have such results, by how much does the vaccine reduce the chances of getting infected with COVID-19? That's, of course, what we are after. And the first caveat that we have to bear in mind is that, as far as we know, only symptomatic participants were tested. So therefore, the best that we can hope to find out is by how much does the vaccine reduce the chances of getting symptomatic COVID. But that's still a very interesting question, so that's the question that we will investigate. Okay, so maybe the most straightforward approach for such an estimation would be to say, let us try to estimate how likely you are to get sick if you have the vaccine, and how likely you are to get sick if you didn't get the vaccine. So so we want to estimate the risk with and without the vaccine. So let P denote the probability of getting symptomatic COVID without the vaccine, and Q of getting with the vaccine. So you can remember P for placebo and Q for vaccine. And we try to estimate those probabilities. And the question is how confident we be about those estimations based on just the results of the experiment as we know them. So it turns out that this approach of trying to estimate P and not trying to estimate Q is not going to give us confident results. Why is that the case? So now I'm bringing my first simple tool from probability theory, which is the Hovding inequality. So the Hovding inequality compares two things. It compares empirical evidence to true expectations and asks by how much can empirical data deviate from the true expectation. So here we denote by X the difference between the empirical average, the percentage that we see in the experiment, and the true expectation. And we ask what is the probability that this difference between what we see in the experiment and the true probability will be greater than epsilon. And if you look at this formula, it is 2 to the e minus 2 epsilon square m. But the main thing, the denominator is just a normalized term. It just tells you what is the range of your random variable. Here, the range is just a probability. It's between 0 and 1, so we can ignore the denominator. So epsilon is the deviation between the experiment and the true mean, and m is the number of participants. So what we should note here is that there is this bound give us no confidence if m, unless m, the sample size, is greater than 1 over epsilon square. Because you see what is happening here. Epsilon square is going to kill m. And once we have here something that is in the range of 1, we have the probability of such big error is at most 2. It's meaningless. We want probability of error to be less than 1. So we need the sample size to be at least 1 over the potential error that we want to protect against. So what does it mean in our experiment? In our experiment, in the Pfizer experiment, we have 8 vaccinated sick people out of 44,000 and 86 sick people non-vaccinated out of 44,000. And we want to know, is this difference meaningful or not? The difference that we see in the experiment between being vaccinated and not being vaccinated. So it's easy to see that the difference between these two numbers is roughly 1 over 550. So we want to ask what's the probability that our experiment will be off by more than this difference, because then if the experiment doesn't distinguish between these two numbers, it doesn't tell us the difference between being vaccinated or not. Now, what did we see here? That if you want to have a confidence in a distinction of epsilon, you need sample size of 1 over epsilon square. But here, 1 over epsilon square, 1 over epsilon square is 550 square is 300,000. So we don't have enough participants. And even in the Moderna numbers are a little bit better. The population that they did the experiment is smaller, but still, to get such a meaningful, to distinguish if the difference between vaccinated and not vaccinated that they see in the experiment is meaningful or not, they would have needed 125,000 participants, and they only have 30,000. So what I'm saying is that this approach will not work. We cannot reliably, based on this number, evaluate what's the probability of getting sick if you are vaccinated and what the probability of getting sick when you're not vaccinated. But still, we can do something. So what are we going to check instead? So there is a notion of the protection ratio of a vaccination. It is measures the efficacy of the vaccine. And what is the protection ratio say? It is, you look at your probability of getting sick without the vaccine minus getting sick when you got the vaccine, and you look at this ratio with the probability. So it asks, by how much did your probability of getting sick went down compared to your probability of getting sick if you didn't get the vaccine. So this is called the protection ratio, and we want to estimate this protection ratio. And if we look at the numbers, this is exactly the numbers that they published. So what they published, the empirical estimates of this ratio. For the Pfizer, there were 86 non-vaccinated sick people, 8 vaccinated sick people. You look at this ratio, it's exactly the 0.9, the 90% success that they published. So what they published is just the average in the experiment. And the same for Moderna. They had 90 patients who were sick without the vaccine and 5 patients sick with the vaccine. The ratio is 0.944, and they published this number, the success probability of our vaccine is 94.4%. You can see already that something here is a bit, how significant is this 94.4? It would have changed a lot if you had one more patient sick or not. So these are the empirical estimates, but what we care about is what is the true population values of these ratios. Okay, so they published the empirical estimates of these protection ratios, and we want to know what is the true population of these values of these ratios. And now we are going to use a different tool. We realize that we cannot directly estimate P and Q because we don't have enough participants. So instead, we will use the Bayes law. The Bayes law is a very useful and very simple trick. So what is the trick of the Bayes law? So I call it the Bayes trick. It's rather than trying to directly estimate the probability of getting sick given that you were vaccinated, we switch it and we say, what is the probability that someone is vaccinated given that they got sick? And what we gain here is that now our denominator is the number of sick people, which is much smaller than before. The denominator was the number of people in the experiment. So this is the Bayes trick. For our case, what we have is that we want to estimate the probability of being vaccinated given that you got sick. So here, let's have a probability space, and we have 2 events A and B. We know that the probability of A given B is the probability of A and B happening divided by the probability of B. This is the basic Bayes formula. And in our case, let A denote being vaccinated and B denote being sick. So A given B is the probability of being vaccinated given that you are sick. So we denote this by V, this probability of being vaccinated given that the person is sick. And we can write the formula that if we knew P and Q, which we don't know, this probability of being sick, being vaccinated, given that you are sick, would be Q over P plus Q. And so let's try to estimate this and see why it's helpful. So the first thing to note, so this is our new V. Remember that R is the protection ratio of the vaccine. That's what we are after. But V is the probability of being vaccinated given that you are sick. So it's easy to do the calculation and see that if you know V, you can easily estimate R. It's just this very simple formula. And also vice versa. If you knew R, you could estimate V. But what have we gained here? So now we moved 2 steps forward. Rather than calculating P and calculating Q, we're trying to get the protection ratio V. And rather than getting the protection ratio V, we are trying to get this value R, the probability of being vaccinated given you are sick. So what did we gain? So just for a sanity check, if R is 0, you see R is the protection ratio. protection ratio, remember, is P minus Q divided by P. So if the vaccine does nothing, P minus Q is be 0, while R is 0. If you put here R equals 0, we get V equals half, which makes sense. If the vaccine does nothing, the probability of being vaccinated, given that you are sick, is exactly half. Half the patients are vaccinated, half not. So it passes our sanity check. And this V that we want to estimate, the new variable, the probability of being vaccinated given that you are sick. You're sick is two types of sick people we have, those that were vaccinated and those that are not vaccinated. So we want to estimate, this is our V. You can view it as if you are just, we want to estimate those probabilities in the population. So we can view it as if we have a coin, and on one side of the coin, it's vaccinated. On the other side of the coin, you are not vaccinated. And this P over Q is the probability that you will see vaccinated when you toss the coin. So this is a very simple and basic variable that we know how to estimate. So this value V, is just the bias of such a coin. So now we can use tools for estimating the bias of a coin based on tossing the coin several times and counting heads and counting tails. So another point to note is that V has the same range. So you remember in our formulas of confidence, it was important to see what is the range of your variable. But V is, again, it goes between 0 and 1, like P and Q. But this number is much bigger than either P or Q. So approximations which are more loose will still be meaningful. So I have here a small comment. I mean, if we view it as a coin toss, we have to ignore to allow repetitions. But the difference between tossing it with repetitions or without repetition is negligible with these numbers. Okay, so now we turned our problem into a simpler problem. We have a coin that each time you see a new patient, it tosses the coin to decide whether the patient was vaccinated or not, and you try to find the bias of this coin. So now we can try again the same Hofding bound that we saw before. What is the probability that the difference between the empirical result that you see and the true bias of the coin is greater than epsilon? So it's the same formula exactly. I just didn't put the A minus B because it's 1. And if we try our numbers, so say we want to check how likely it is that we will see such results if the protection ratio of the vaccine is 0.6. Again, what it does mean protection ratio 0.6 is that the difference between your probability of being sick without the vaccine and with the vaccine is 0.6. So if the protection ratio is 0.6, by this simple formula of translating between protection ratio and our bias of the coin, we get that it corresponds to a bias of the coin being 0.285. And now if we look at our sample size, because now we toss the coin not for every participant in the experiment, we only toss the coin for every participant that got sick. You see, we turned the problem on its head. Given that someone is sick, we check whether they were vaccinated or not. So we only have 94 experiments or coin tosses. And the sample average, the average of the sample, how many heads did we see in the experiment, is 8 out of these 94 in the Pfizer experiment. So the gap between this and our assumption that it should have been 285 is roughly 0.2. So this epsilon is 0.2, and we can calculate what happens when you put here 0.2. And we see that the result, the probability that the protection ratio of your vaccine is 0.6, which is pretty good. About 4.5 is already considered effective vaccine. The probability that your protection ratio is 0.6 and you got such a result is very small. So it tells you that likely your protection ratio was higher than 0.6. So this looks very encouraging. This says the probability that we got those results just by chance is pretty small. It's pretty safe to trust it. But there is one more thing that we have to bear in mind. I mean, on first sight, this seems pretty reassuring. It seems highly unlikely that a vaccine that is not protective up to 0.6 will yield such nice experimental results. But there is one more thing we have to bear in mind, which kind of shakes this confidence a little bit. And this is the fact that there are about, right now in the world, about 2,000 clinical trials of vaccines and treatment are being carried out. And of course, nobody announces when they don't succeed. They only announce if they succeed. So even if each of them is useless and it has success probability below 0.02, the probability that at least one of them will yield such a good result by pure chance is highly significant. Because there are so many experiments happening around, and you will just see only the one that made it. I mean, it's just like all those journalists that tell you that there is this small county in Ohio that in the past 50 years always predicted correctly who the president will be. But there are so many counties that even if each county just tosses a coin, one of them will survive all the elections of the last 50 years. So in the same year, how do we know that it's not pure chance? And because we have so many clinical trials running in parallel, this is just by chance one of them that made it. Or now we know two of them that made it. Okay, so we need to look a little bit into another very basic notion in statistics, and that's the notion of p-values and Bonferroni correction. So just recall, the p-value is exactly what we are looking at here. It's the probability of obtaining the test result that you saw, given some null hypothesis that is correct. So very small p-values means that it's extremely unlikely to be just chance. So we want to have small p-values. Here, the null hypothesis is that our vaccine is not really helpful. So the question is, what is the probability that we will see such beautiful result if the vaccine is not really helpful? Its protection ratio is below some R. And now what is the Bonferroni correction? It aims to address the risk of cheating by running many experiments and cherry picking the one of them that was most extreme. So how does this statistician Bonferroni suggest to correct it? And it's pretty safe correction. He says multiply your p-values by the number of experiments. If you want to be confident, don't just take this 1/44, but think there are 2,000 experiments running in parallel. If each of them had just probability of success 1/50, the probability that at least one of them will look wonderful is 1/44 times 2,000. Now it killed our estimate, because now our confidence degraded. Rather than the probability of having such a result just by chance being 1/44, now it's almost certain that if you run 2,000 experiments, one of them will be so successful. So how can we get out of it? So it turns out that we have better bounds than the Hofding bound. So we use just the Hofding bound. So luckily, we have bounds that are more tighter on those probabilities. Because remember, what are we trying to estimate? It's a very simple experiment. You have a coin, You assume that the bias of the coin is some V. You toss the coin, you count heads, and you want to see how likely it is that you got such a result. So that's a very common experiment, and we know very well how to estimate such extreme probabilities, such tail probabilities. So one common approach is to approximate it by a Gaussian. If I toss a coin and I count how many times I saw one head, two heads, three heads, and so on, as the number of tosses go to infinity, we get a normal distribution or a Gaussian distribution whose mean is exactly the bias of the coin. And we have tables that tell us if you have so many standard deviations away from the mean, how likely it is that your experiments will yield such a result. And we can estimate of course, it depends on the variance or the standard deviation, and simple formulas for this. So to my students, I encourage them to try and see what do you get from the Gaussian approximation. Calculate the variance of this variable V based on 94 many experiments, and look at the table to see how likely we are to get such results. But I was even more lucky than that. I had Nati Srebo, and he ran a Python program that calculates those exact probabilities. It's not such a formidable task because we only have 8 heads. So we just want to see what is the probability of getting at most 8 heads if your coin is not really biased. And here are the results that I got from Nati. So let us look at what this table shows us. So here we have the assumed protection ratio. So if we assume that the real protection ratio of the vaccine is one of those numbers that we see in the x-axis, and this will be the p-value. So this will tell you, if you assume that the protection value is 0.65, say, so the green one is after correcting for these 2,000 studies running in parallel, and the blue one is without the correction, but without the correction, it's not really meaningful. So we look at the green one. So what does it tell us? It tells us that if the protection ratio were not at least 0.65, the probability of seeing results as we saw will be less than 1/20, which is considered pretty safe. So, and of course, if we only care about protection ratio 0.6, it's already pretty good. You see that the probability of getting such results by just chance is really, really small. It's 1/200. So we can say that pretty safely, with these results, the protection ratio of the Pfizer vaccine is at least 0.6, depending on how certain you want to be, and very similar results if we apply them to the Moderna experiment. So the bottom line, I mean, there are many clinical issues that remain open, and it's not, as someone else says, I'm not a doctor. I mean, I won't get into the clinical things, but of course, I mean, you can think only symptomatic participants were tested, so maybe the vaccine only suppresses symptoms. Maybe you would get similar results with just T and vitamin C. We have a result given at a certain point in time. Maybe the vaccine just delays the onset of the symptoms. And it's unclear what is the relation between the efficacy of the vaccine and the risk group of the patients. I mean, Moderna told us what percentage of the people in the experiment were in risk groups, but they didn't say exactly what percentage were of the sick, vaccinated and not vaccinated were in the risk group. So there are many clinical questions. I will not get into it. All I wanted was to clarify the statistical aspect. And the statistical conclusion is that from a statistical point of view, the results are highly significant. So we can be optimistic, and it's very unlikely that there would have been such a result if those vaccines were not really effective. So yeah, that's a story that I wanted to tell today. I'm happy to get questions. Yes.
Shai,
Dan.
there is some on the chat channel as well. You might want to check.
On the chat.
Amir, can you show your face so I can read your lips?
Just a second. So what do we have? So Danbury asked, can a known rate of being symptomatic be used to improve the estimates? So yeah, I haven't looked at it, but it's not clear because what we don't know is maybe the vaccine changes your probability of being symptomatic.
Okay.
Yes.
Okay. The thing is, my niece, a biologist, tried to explain something. And okay, I'm not a medical doctor, I'm not a biologist, but my understanding is that they had reason to believe that all of the vaccines would exhibit a similar protection ratio because they are similarly designed. They are not independent of each other.
Right. But
so in a sense, what you've been treating as an independent test.
No,
not an independent test.
I was not treating it as independent. I was looking only at one. I was analyzing only the Pfizer. The fact that we have on top of it the results of Moderna only strengthen it because it's a similar methodology. But it definitely doesn't weaken the results of the Pfizer. The fact that they are, so it only strengthens. The question by how much it strengthens those results depends on how dependent they are. But it can only strengthen the results.
That was my question. If they are designed similarly, then...
If they are the same, say the extreme case, they are the same vaccine, so it just means that we have more sick participants, the experiment is bigger, and we can trust the results even more. You can just throw them to the same bucket, and then we will be even more confident of our results.
Okay, thank you.
Sadria, do you want to turn on your video and ask your question?
Hi, can you see me? I don't know.
Yes, yes.
Okay, so I didn't understand that part that you talk about base probability, that on the denominator you had PB. So that's the part, that's the probability that you are sick and you take the vaccine, right?
On the denominator, I have P plus Q. I have, on the denominator, I have all the sick people. And on denominator, I have the sick people that got the vaccine.
Oh, so you consider that you take the vaccine given that you're sick?
That you got the vaccine given that you are sick. Since we distributed the vaccine randomly, I can just look at the pool of sick people and ask which fraction of them got the vaccine.
Oh, okay. So maybe that's my misunderstanding. So I don't understand. So when you're sick, why should you take the vaccine?
No, it's not when you're sick. It's not. It's the question is not when you take the vaccine when you are sick. They did the experiment.
Yep.
They have people that took vaccine, people didn't take the vaccine, people that got sick.
Yep.
Now they ask, from those people that got sick, how many of them have the vaccine?
That's right.
You can view it as a coin toss, since the vaccine was distributed randomly, and the bias of this coin is this probability of having got the vaccine in the past, given that you are sick now.
Oh, okay. Thank you.
Okay, let's see what we have here. Tosca, do you want to turn yourself on and ask the question?
Hi. Yeah, so I was wondering if the publication of results was at a predetermined time.
Yeah, that's a very good question, because if you can always maybe choose the stopping time when your results look wonderful.
Yeah.
And we don't really know how they choose their stopping time, and that's a very good question.
So they didn't announce any of
Yeah, no, they didn't say in advance. They said in advance, I mean, Pfizer said in advance, we will publish results once we have 60-something sick people, because they administrate the vaccines, and then they have to wait to see how many people got sick. Without sick people, they wouldn't know anything. So in advance, they said we will publish the results when we get 60-something, and at the end, they published when they got 94. And you can ask, why did they pick the number? I have my conspiracy theory about it, but because the CEO sold his stocks in Pfizer 1 or 2 days after the results. And he cannot decide, I mean, it's inside information to sell your stocks after you see the results. So he must have scheduled the selling of stocks beforehand. And it could be that he published the results just before the day that he's scheduled for selling the stocks. But this is very good from the point of view of the experiment. It means that the scheduling was independent of the actual results.
But Shai, I thought it wasn't Pfizer who was saying the numbers. It was an independent panel who got the numbers. They gave Pfizer the final results of the experiment.
No,
and
no,
allowed
but the
them
result,
to publicize. It wasn't Pfizer who analyzed the data.
No, it's not about analyzing. It's a question of when do you stop and count? Because if you wait another week, more people will be sick. And the number of vaccinated and unvaccinated among them will be different. It changes every week. Anybody else has a question here that they want to ask? Alan? Am I here?
So given your calculation, is it possible that they can reverse engineer to find out how many patients they need for it to be a successful vaccine, or how many?
They did. Yeah, they did, and they claim that there will be certain enough about the results to pass some regulations once they have 160 sick patients. In that respect, both experiments are the same, because they are both looking at the ratio among the sick people. So we are waiting to have roughly 160 sick people, and then we will be able to be more confident of the results. Yes, Ida?
Yes, hi. So my question is in slide 15.
Yeah, I don't have the numbers of the slides.
Yes. Can you go forward? You are on 8 now. 9, 12, 13, 14. One slide before this.
The graph?
Yes, this one. Yes.
Okay.
Yeah, so my question is that what happens that the protection ratio increases, and does it matter to consider these changes, these underlying changes, to be able to compare the points in the curve? Like in the green curve, you were comparing the point for 0.6 and 0.65, right? So I mean, is it fair to compare these given the underlying reasons behind the changes for
So the point is that, I mean, what is your null hypothesis? If my null hypothesis is that the vaccine is very protective, say 0.7 or 0.75, then the probability of seeing such results I mean, that the vaccine is not so, now I confuse myself. Yeah. Given the assumption that the vaccine is not very, very protective, will not rule out such results strongly enough. So we want to be conservative in our assumptions of the protectiveness. You see, as the protectiveness grows, the likelihood of seeing our results grows also. And we want to ask the likelihood of seeing our results by pure chance if the hypothesis is not correct. So we want to be in a situation where if the hypothesis is not correct, the likelihood of seeing such results is very small. And this gives us confidence on the correctness of the results.
Thank you.
The more conservative our assumption is about the protection, the more can we be sure that it is at least that much protective. Yeah, maybe it's need a little bit more, digesting it, but it's a very simple argument.
Okay, thank you so much.
Can I ask one more question, Shai?
Sure. Yeah, go ahead.
Yeah. So given that you've now asked the flip question of how likely is it that someone got a vaccine given that they are sick, is it possible to, what can I tell my non-math, non-computer science friends if they ask, what is the chance that I am going to get it, that I have a vaccine? Do I just say you have to trust the math and think that it is going to work? Or?
No. I mean, that's what we saw in the beginning. We cannot estimate reliably your chance of getting sick. But what we can tell them with confidence is this protection ratio. So where do I have the protection ratio?
Yeah, I mean,
I don't get it now. This protection ratio. So I don't know why my screen. Oh, yeah. So this I cannot tell you what's your probability of getting sick if you get the vaccine or not, but I can tell you by how much it improves if you got the vaccine compared to not having got it.
Okay.
That's what you can tell your non-mathematician friends.
Okay.
Yeah.
Okay.
Okay. So thank you for attending, and I hope that it was meaningful in spite of being so trivial. Yeah, Dan.
Oh, I'm just.
Oh, okay. Yeah.
Yeah.
Okay. Yeah. Yeah. Thank you very much. Nice to see all the faces.
Thank you.
Hope to see you again in real life soon. Bye.
Thank you.
Bye.
Thank you.
חיים ארוכים ושגשוג. לבריאות.
Bye.
Bye, everyone.